Hierbij open ik deze academische zitting aan de Universiteit Maastricht. Mijn naam is Ton de Groei, ik ben de prorector van deze academische zitting en voorzitter van de promotiecommissie. Allereerst heet ik van harte welkom mevrouw Maxime Verwoert. Zij zal in het openbaar verdedigen haar proefschrift en dat is getiteld On the Neural Symphony of Speech, Decoding Speech Production with stereo-electroencephalography. Welkom alle leden van de promotiecommissie. In het bijzonder heet ik welkom de 3 promotoren die tegenover mij zitten. En dat zijn dokter Pieter Kubben. Hij is professor of neurosurgery. Professor Dr. Temel. Hij is ook hoogleraar neurosurgery. En dokter Herf. Hij is, heeft als expertise neural engineering en ze zijn allemaal verbonden aan de Universiteit Maastricht. Ik heet u ook van harte welkom hier in de aula en ik heet ook van harte welkom alle volgers van de livestream. Ik heb nog een mededeling voor u. We gaan ook met verschillende talen werken. U zult direct een overzicht krijgen van het proefschrift in het Engels. En ook de oppositie zal ook plaatsvinden in het Engels. Dat komt ook omdat we buitenlandse gasten hebben. Dus ik zou u willen verzoeken, mevrouw Verwoert, om een samenvatting te geven van uw proefschrift. En ik wens u veel succes in het komende uur. Gaat uw gang.
Thanks. Good afternoon, Pro-Rector, the members of the Defense Committee, my supervisors, and my colleagues, friends, and family. I will gladly take this opportunity to present to you the work of my dissertation, taking you on a tour on the neural symphony of speech. And because I couldn't resist, there will be some heavy metal references along the way. So our voice, it's our most powerful instrument. It makes us able to speak, and that lets us communicate our thoughts, our ideas, and our emotions onto others with ease. It is the most fast and easiest way for us to communicate with others and also to connect with others. The problem occurs when this ability to speak is disrupted due to disorders or diseases such as a tumor or a stroke or a neuromuscular condition such as ALS. And one such person who currently still lives with ALS is the great heavy metal musician Jason Becker. He is not able to move except for his eyes, and that allows him to communicate with his family very slowly and even compose music, although with a lot of effort. And of course, I couldn't leave out another person who lived with ALS, and that is the great physicist Stephen Hawking. And even in his late years, he still managed to write books and speeches using a residual muscle in his cheek. But unfortunately, many people with ALS end up in a locked-in state, and then they're completely unable to communicate at all. So wouldn't it be wonderful if there would be a technology that would allow these people to still communicate without a lot of effort, despite their disease? And that is why we are working on a system, the brain-computer interface, or BCI. This is a system that records neural signals directly from the brain and transforms it, usually with computer models, into an output that a person can use to perform an action. And the first BCIs were developed for movement. So for example, a person could use their thoughts to control a robot arm or their wheelchair, for example. And this has been in development for many years. But more recently, the field has progressed towards speech BCIs. So the system or the process is the same, except the output is now something that people can use to communicate. So for example, this can be text written on the screen, or it can be directly transformed into speech sounds, as we like to focus on. So for example, a person only has to think about saying hello, and then the computer will say this for them. And this can be applied to many individuals with speech impairments. Now, in our lab and in my work, we focus on a technique called stereo-electroencephalography, or SEEG. So very small, thin wires are implanted into the brain, similar to the strings of a guitar. And along that wire are electrodes. And these electrodes, they record the neural activity from that location. This is what it looks like in a real brain. So you can see that electrodes are widely distributed across the brain and also reaching deeper areas. And this is the unique advantage of SCAG, because other neurotechnologies, they usually lie on the cortical surface of the brain, and they cannot go deep. This is what it looks like in an individual actually implanted with those electrodes. And these are drug-resistant, or people with drug-resistant epilepsy. They're routinely implanted with this technique in order to detect their epilepsy. And we then ask these participants to participate in our speech studies. So it's important to note that these individuals are still able to talk. So the research that I present here is fundamental and can hopefully one day be applied to individuals who can no longer speak. Now, the first thing we needed to figure out is, that's a bit too far, if we can use these SCAG signals for speech. So do they actually carry enough speech-related information? So for that, I recorded the neural data and speech data from 10 individuals. And we can see here what it looks like. So I trained a model, a linear regression, to transform these brain signals into speech. And on top here, in A, you can see the spectrogram of the original speech of a participant, and next to that, its waveform. And below that, we have the reconstructed ones from the model. And you can see temporarily, it's working quite well, except the very small details, they are not that well captured. And this was the case for most of our 10 participants in the study. Importantly, the performance was all above what was expected by chance. And even more importantly, we published this data set and made it openly accessible so that other scientists and students could work with this data as well. So you can kind of see this as our demo album. And since its release in 2022, many people have actually downloaded this album. Here you can see how it's been used around the world. So many scientists, most of them, have used this data set to develop new and improved artificial intelligence models to improve the speech reconstruction. And you can see it mostly has been used in Europe, including 4 papers of our own, then in China, and even one in Australia. And this is besides many student projects as well. So there's another important aspect to speech BCIs. It needs to work in real time. And for that, we developed a system that can transform the neural signals into an audible speech sound very, very fast. And that is within 40 milliseconds. And this is important because in order for us to speak smoothly, we need to continuously get feedback. And that allows us to improve when we make a mistake, for example. But we also need to hear it within this time frame in order to perceive the speech as if it were our own. Otherwise, we would think it's maybe from someone else. And this can be applied to music as well. So for example, when you're playing an electrical guitar, you need to hear the sound coming from the amplifier almost immediately, or it would disrupt your playing. So now that we've established the technical feasibility of SCAG, I want to shift the focus to its unique advantage, and that is that we are able to capture signals from all over the brain. And then we can answer the question, where in the brain can we decode speech? So for that, I collected more data, this time from 30 participants. So we get electrodes from even more areas in the brain. And then we can compare different anatomical features. I won't go over all of them, but one important thing is the gyrus versus the sulcus. So the gyrus is a region of the brain that's kind of lying on the outer surface. And this is what most other neurotechnologies actually capture. Then we have the sulcus. The tissue is pretty much the same, but it goes into a groove into the brain. and SEEG can capture these signals, but others cannot. In this work, I trained a simple binary classifier to detect the difference between speech and silence. And then we can look at the performance of different areas. And we do not see any significant difference between the gyrus and the sulcus. So that tells us that there's valuable information within the sulcus as well. Besides that, we also found a lot of good speech-related activity from white matter signals in the brain. And these are the connections in our brain, and they lie deep within the brain as well. When we look spatially, we can see that the best results, so in the darker color, are localized in the central parts of the brain, in both the left and the right side of the brain. And it basically comes down to regions in the temporal lobe, the motor cortex, the supramarginal cortex, and a region that is even deeper inside the brain called the insula. So now that we know a little bit more about anatomy, we can break down the speech signals even further and figure out what type of speech can we decode where. So this time, I analyzed the data in 3 different ways, each capturing a different aspect of speech. We call this a feature. In the first, I used a pre-trained acoustic to articulatory inversion neural network model that could let us extract articulatory trajectories from the speech signals. And this is essentially our mouth movements. Next, I used a short-term Fourier transform to capture the acoustic properties of the speech. This is essentially the sound. And finally, I used the word-to-vec language model, basically a predecessor of ChatGPT, to extract semantic properties. And what is semantics? It's basically the meaning of words and how they're associated. So for example, when we think of a dog, we might also think of a ball, or a bone, or love. And these are all associated, at least in my case. And this is what's captured in the embeddings. There's a numerical representation of this. And we can use this to train models. So I trained a linear regression to then reconstruct the neural signal based on these features. And now that we have all these different signals, we can correlate that with our neural signals and figure out how these are represented in the brain. And we found out that the acoustic and the articulatory features are very much correlated with one another, and they're very much overlapping. So you can see that in yellow in the picture here. And we can also see that in both the left and the right side of the brain. But you can also see that in blue, it's quite different. So in blue is the semantics, and we can see this is much more widespread across the entire brain. So this kind of, and there's no overlap, or very little overlap with the other 2 features. So this tells us that it might live in a separate network. We can also see that all of the features are more widespread and also temporally dynamic in the left hemisphere compared to the right hemisphere. So now that we know even more about anatomy and speech, it's maybe a good time to discuss the cover on the front of my thesis, as well as its title, because you might have been wondering what that's all about. So, taking the broader literature and my work together, I believe that almost the entire brain is involved in this highly complex process of speech production. So many regions need to work together for us to produce speech, such that many musicians need to play together in order to create a symphony of sound in an orchestra. So I will continue with this musical analogy to explain how speech happens in the brain. So let's start with the visual cortex. This is the part in the back of the brain that lets us process things that we see. So also when we're reading text, for example, this is where it's first coming in. But when we do not have text to read or a musical score in front of us, then the frontal cortex takes the role of a composer, figuring out and putting things together on what to actually say or what to play. And this plan gets kind of sent to the rest of the brain, including the motor cortex. And this can be thought of as the string section, because this is what pulls our articulatory muscles that we need to speak. And then we also have the temporal lobe, and this can be thought of as the musical scores themselves, because this region is mostly involved in processing and also predicting the actual sounds that we want to produce. And finally, we have the supramarginal cortex. It can be kind of thought of as a conductor, because this is a center where everything gets integrated and make sure that everything is working well together. So to conclude, the entire brain works together to produce speech. This includes regions beyond the cortical surface, so think about our sulci. Stereo-EEG is a great tool to study brain-wide neurodynamics in speech production, and this is good for both neuroscience in general and for neurotechnological development. And finally, speech neuroprosthetics can one day restore lost voices. I now give the word back to the prorector.
Thank you very much, Mrs. Verwoert, for a clear summary of your thesis. The opposition will be opened by the chair of the Thesis Assessment Committee, Professor Bernadette Jansma. She is Professor of Cognitive Neuroscience of Language at Maastricht University. Professor Jansma.
Thank you, Prorector. Dear candidate, first of all, let me congratulate you and also your supervisor team. I read your thesis with great pleasure. And just allow me some keywords where I think I'm impressed, and hopefully everyone. So you work very interdisciplinary. I think you bridge here with ease linguistics, cognitive neuroscience, engineering and medicine. I think that's something. You publish in international journals. You foster open science, and you are very checking methodological aspects with rigor. In chapter on referencing, another chapter on contribution of others than the motor cortex, extending to cortex, real-time decoding. I think this is very impressive, and you can be very proud. Chapeau. But of course, I also have questions, and that actually relates a bit to the first one relates to chapter 2, and there you use, and actually everywhere you use reading of words. And I just would like to tease you now a little bit and would say this is not speech production at all. This is reading aloud. And you can also read without conceptualizing meaning, because you can also repeat stupid non-words with ease. So what is your view on how actually related is your neural signal that you record so nicely actually is production?
Highly esteemed opponent, thank you for your kind words and your question. Indeed, this is one of the limitations of the setup that we started out with initially. Reading words, it's good for in terms of being able to classify and doing kind of the engineering part and the analysis for it. But indeed, as I explained, when we're just reading, we do not really need the frontal cortex, for example, because we don't need to generate it really ourselves. We don't need to think about it as much. So it's just copying in a way. In our case, we are really interested in the speech production itself. So even the producing, so using our motor cortex and producing sounds itself, even if we haven't generated it ourselves.
I get that. So, but would you envision feasibility to actually use other stimulation that actually then triggers a true production like pictures? Would that be feasible with the patients, and how would you envision that?
Yes. After the initial studies, we actually changed the paradigm as well. So first we went to sentence production, a little bit more complicated, but still reading. And then we moved on to indeed showing a picture, a scene, and let them describe the scene. So then they really have to come up with their own words. So there would be a lot more linguistic information in the brain, and there would be a lot more areas involved as well, I would say.
Okay, nice. Thanks a lot. I have a bit more time, I think. A next question would relate to the signal that you use for the decoding. Basically, it's an average signal. And in chapter 4, I read in the methods, it's a bandpass of 70 to 170 hertz that you use. that's quite broad. And actually, when you look into surface EEG, functional relevant bands are lower. So that would be like theta between 3 and 7 hertz and alpha between 8 and 15 hertz or something. So how does these higher frequency bands in deep recordings actually relate to surface EEG frequency bands? That's one question I have.
Okay. The reason why we choose the high frequency signals is because first we're able to capture them, which is not possible with surface EEG. And this frequency range has been well established to coincide with the firing rate of neurons. And it's been the most useful feature in the speech literature in terms of intracranial signals.
Yeah. And then just out of curiosity, and then I'm done, so if I look into surface EEG and while people are naming pictures, I see theta synchronization right from the onset of the picture and alpha desync. And we have functional interpretations for that. One is more related to attentive selecting the picture, and the other one probably is engaging the language network for that. Do you see anything of this type in your neural signal as well, that one could compare the two worlds?
I think from other literature there is similar findings. We have actually chosen to not focus on the low frequency signals because the high ones are in general from our first initial test, when we look at different frequency bands, these were very much stronger. And I think that's because it just captures a lot more about the general process of speech versus silence, for example. And I think we would need more sophisticated language tests like you would normally do in EEG, more hypothesis-driven tests to really uncover these more specialized functions that are probably more in the lower frequency ranges and also probably stemming more from subcortical areas potentially.
Yeah. Oh, thanks a lot. I give the word back to the prorector.
I have a little bit more time if you like.
I do?
Yes.
Yeah? Okay, that's nice. Thanks. Related to the differentiation between language production and reading again. So what we see in free reading is that free speaking is that people conceptualize. So basically you have an internal idea and you pop out your ideas via the mouse. And what people have discussed is that there is a lot of interaction between the angular gyrus and the hippocampus in initiating this rocket actually to fly. And I was wondering, you have mentioned in your thesis a couple of times that you have a lot of data from the hippocampus. Is there any chance to see whether actually you use actively your model? Does this actively use hippocampus information to support decoding or not? Would you, if no, would you incorporate hippocampus? Do you see a system now?
Yeah, we do see it one of the regions that, in terms of the subcortical structures, it seems to be clearly involved, except not to the extent that we were expecting it in terms of a brain-wide resolution. And this could be in part because we're focusing on these high-frequency signals.
Yeah.
And the specific location might play a role as well. And this is not something we were in control of. Of course, that was a limitation of the study as well, that we did not have consistent sampling across individuals, which makes it quite difficult to really zoom into a specific region and figure that out. I think that's definitely something to explore in further research, also with lower frequency ranges, if we can detect more from the hippocampus.
Okay, thanks a lot. Thanks.
Thank you, Professor Jansma. The next opponent is Professor Simon Jacob. He is Professor of Translational Neurotechnology at the Technical University of Munich in Germany. Professor Jacob.
Thank you, Pro-Rector. Dear candidate, let me agree on congratulating you for this fantastic work. I can only see it, the culmination in writing, but I can only imagine as a scientist and clinician myself how much work this must have been, and congratulations as well to your supervisors and promoters. This is a great pleasure for me to be here, and I do have questions. I think one of the biggest merits of your work was the spatial coverage and your unbiased approach. And looking at different parts of the brain that might implement one of the most human of our cognitive functions. So let me start by asking you why you emphasize so much the difference between the gyrus and the sulcus. Has there ever been any person in neuroscience who believed that the sulcus was less important than the gyrus?
Highly esteemed opponent, thank you for your kind words and your question. Indeed, I do not think there is a big discussion on that, because I have found some papers that there is some cytoarchitectural differences between the gyrus and the sulcus in terms of how the neurons are positioned. That's just because the grooves just form differently, so need to position themselves differently, the orientation-wise. Other than that, it's an extension of one another. It just happens to fold that way. So I do not believe there's a real discussion for it, except that it has not been studied because other technologies just haven't been able to capture it. So this is something we wanted to really highlight and focus, that there's a lot of unexplored territory there in terms of BCI systems that could have a lot of potential.
Okay, thank you very much. Let's continue now on your spatial coverage. So I thought it was fascinating as well to see an unbiased approach that includes the other 50% of our brain that is typically not in the focus of language and speech, which is the right hemisphere. And I was very pleased to see your meticulous approach here and comparison of left and right. I was quite surprised to see, and I would say pleasantly surprised to see, that the right hemisphere played a large role in your studies. And you found, I would say, on a face value in terms of data, quite a good correspondence between left and right, and I wouldn't call it a symmetry, but it was getting close to that. And now as maybe a clinician as well, and looking at our knowledge of the lateralization of language from a behavioral point of view, wouldn't you agree that there was some form of disconnect here between how we see the brain to be lateralized in the sense of language, but on your data approach you see much more of a similarity between left and right? Could you please enlighten me here on this point?
Yeah, I very much agree. I think the whole field has mostly focused on the left hemisphere. In fact, there's many studies who completely leave out the right hemisphere, even though they might have been able to capture signals from there. I do still believe that the left hemisphere is mostly dominant. So in our work ourselves, we also found that it was much more dynamic and more widespread in the left compared to the right hemisphere, but especially the core language regions that we need for us to speak or hear sounds. So the motor cortex and the auditory cortex, they're very much bilateral. And this makes sense too, because when we're speaking, we need to use our full face, not just half our face. And so that's one of the reasons. Except there were some differences too. So for example, the supramarginal gyrus, I mostly found that involved in the left hemisphere and not so much in the right. And then the insula, mostly in the right and not so much in the left. And that could be because of the spatial coverage, because they're not exactly symmetrical. So I can't draw too much conclusions on that, but I did think it was an interesting finding.
Was that true on the population level, or was that also true on the single subject level? Could it be that individual subjects are more or less lateralized, and the regions that you mentioned were like oversampled in by chance subjects that happen to be more insular dominant and other subjects that happen to be more supramarginal gyrus dominant?
That would be possible. We have not looked at this because for most individuals, they did not have bilateral coverage. So you're not able to directly compare the two hemispheres with one another. In some regions, yes, for example, the hippocampus is often sampled bilaterally. We haven't looked at this specifically, so that is definitely something that would be interesting to do.
Thank you. Let's go to the inferior frontal cortex, or the inferior frontal gyrus. I was surprised to see that was a lame brain area somehow in your data set. This, of course, relates very strongly to what we know about the role of the inferior frontal gyrus, and famously, Broca described this area to be heavily implicated in language production, and you are at least studying the production of speech sounds. So I think you found a little bit of a semantic representation in this brain area, but very little articulatory and no acoustic. That clashes with my view of what the Broca area is supposed to be doing.
Yeah, I think that's been a kind of a big discussion in the field in recent years, that this area has been kind of needing a redefinition. I do believe it's not so much involved in the production itself, but more in, for example, the syntax and integrating syntax and semantics. And this is something that you need to do when you're really generating the speech, and not so much when you're just copying or doing repetition, for example, or reading like our participants mostly did. I think this is the reason why we didn't see much activity in that area, because people were just reading, so they didn't need that frontal cortex. But in a more complicated task where people needed to read sentences, they needed to think a bit more, and they needed to put their words together, and there we did see some activity there. So I think it's more this linguistic process and not the producing the speech itself.
Would you be able to relate your neural signals to like some successful or unsuccessful behavioral outputs? Were there instances where you could see that like a mistake or a phonological error in speech production would map to some differences in neural signals? Were you incorporating behavioral measures here as well?
This is something we could possibly do because we have the audio recordings. We have not done so because our analysis really focused on this continuous reconstruction of speech. So we have not really dove into mistakes and how the neural features are correlated to that. But that's definitely something interesting to figure out, yeah.
So thank you very much for your answers. I pass back to the pro-rector now. Thank you.
Thank you, Professor Jacob. The opposition will be continued by Professor Henk van Sandbrink. He is Professor of Spinal Neurosurgery at Maastricht University. Professor van Sandbrink.
Thank you, Mr. Pro-Rector. First of all, I want to congratulate you with finishing your thesis. Of course, I want to incorporate family, friends, and your supervising team. I learned a lot of your thesis by reading it, and I was intrigued by this cover and by the association or the analogy with the symphony. So I want to discuss about the analogy with music. And first of all, I want to, and it is about chapter 5. First of all, I want to ask one of the paranymphs to read proposition number 3.
Semantic speech representations are more widely distributed across the brain than articulatory and acoustic speech representations.
So it is about semantics, I think. And but you use in your presentation also language and speech about voluntary. I don't know why when you do use speech and when you use language. Can you explain about the difference about speech and language?
Highly esteemed opponent, thank you for your kind words and your question. Indeed, I think these words are used intertwinedly because they are intertwined. So we need language to speak, and well, we can use language without speaking. So the other way, it's not exactly. But when I refer to speech, I refer to the process of producing sound or moving our articulatory organs. Mm-hmm. And when we talk about language, there's a lot more involved. So linguistics involves really this generating of speech, really coming up with structures, coming up with words to say. So now I'm really using my language to figure out what I need to say.
Yes. And what do you think? What is more important, speech or language? Do you have a preference for it? Or?
It depends, I think, on the goal, on what do we want to achieve.
Mm-hmm. But you study speech and language, and you give a data set, these 100 words. And are they voluntary chosen, or is it a standardized set of words?
It is a standardized set of words.
Okay.
So this is why the focus is on speech, because as we just discussed, there's not a lot of linguistics that the participants need to come up with themselves. So I wouldn't call it a really language study, more a speech. So this is more the last stages. So when we're really formulating speech ourselves, we need to come up with the words, and all these things are involved. And that's what we're not capturing that well. But the last parts, when we're actively producing it, so we're using our articulatory organs, we're trying to predict the sound and actually producing the sound.
I think that is a bit uniform. But when you offer a composer the same information, notes or they will produce a different symphony, or isn't it? And isn't it the same when you offer the same words, whether they are standardized or not, that the person or the patient or will produce another symphony or another type of electrical information?
It's true. Everyone says even the same word in many different ways. And that's, of course, because our brains are different and so many things can happen.
So how do you overcome this difference? How do you overcome this difference?
I do not.
You don't?
I
Okay.
don't, no, because what we're doing is within one person, we're training the models, so not across participants, and this is actually called transfer learning. This is something that's very difficult in speech, and probably because of this reason, because everyone uses slightly different areas of the brain, or the output behavior is slightly different.
And you made this example by a dog, and I wrote it down. You have an association by a dog with a dog with ball, bone, and love. But maybe I have another association, and it is an involuntary speech, and then this brain-computer interfaces. He says, "Oh, he's aggressive." How do you overcome this? And he is not only lovely.
That is an interesting. That's interesting. Perhaps through personalized models, so really training a system based on a person's own experiences. It could be trained on text that the person has generated before, for example, and use
it will be very difficult.
Personalized language.
Is there a solution in temporalization? Then maybe this association is a bit later. Then you made some hints towards temporalization or
temporal dynamics.
Yeah.
If that process is later?
Yeah, maybe it is later, or maybe it is quicker. But maybe there is a difference in time.
So we have different processes in speech. And I think when we're producing speech, this is one of the first stages, is figuring out the semantics, which words to say. So we need to access this in our brain, and then we can go on to actually produce it. This is the part that I mostly focused on. And when we're, for example, listening, it's the opposite. So then we're first processing the sound, and then we're accessing the semantics and figuring out what do these words actually mean that I just heard. So in that sense, there are differences. And between people, there's also differences because some people are much faster at accessing this information than other people. If that's what you're getting at, I'm not sure.
I don't know. You are the expert. I'm just a spinal neurosurgeon, so I ask myself this question. But thank you for your answers. I will give the word back to Mr. Prorector.
Still, you have some more time.
Oh
yes.
Okay. I look on the clock. Okay. Okay. Thank you. Then I want to proceed advance with the question about left and right. And since I'm a neurosurgeon, I associated always speech with the left side when you are right-handed. Did you check for left and right-handedness, or how do you?
Yeah, this is a good question. This is definitely something we want to take into account, but we didn't have this information for every single participant. So yeah, we did not. But there could definitely be differences. So this would be something, if we get this data, we could look at if...
Then your predominance of the left side is maybe due to a predominance of right-handed persons.
Yeah. And indeed, most of the participants were right-handed. Sometimes we asked or we saw it when they're signing the informed consent form. Okay. So, yeah.
So I see the prorector. I think my time is over now. I give the word back to the prorector. Thank you.
Thank you so much, Professor van Zandbrink. The next opponent is Dr. van Straten. She is associate professor in epileptology, and she is affiliated with the Epilepsie Centrum Kempenhagen in Hezen. Het woord is aan u, Dr. van Straten.
Thank you, Mr. Prorector, and also I would like to compliment you with this really nice work and include the rest of the team, of course. I want to talk with you about the topic of human enhancement and BCI. So go beyond repairing lost function. I think you know that there are certain companies in the world with BCI already targeting that with the ultimate aim of human enhancement, for example, the Neuralink of Elon Musk. And that also brings me to the picture of the front of your thesis. Music and BCI, I think some people have more talent for music than others. I can imagine that you have some musical talents because of your the front of your thesis. How would you look at the human enhancement of musicality? So wouldn't it be nice if every person can enjoy music as much as you do? And how would you go about to establishing that goal?
Esteemed opponent, thank you for your kind words and your question. That is a very interesting question. I have not thought about this before because the focus really has been on restoring lost functions. But indeed, this is something we need to think about because that is definitely coming. How would I enhance music learning or music experience?
Everything related to music.
Yeah, I think in terms of learning an instrument, for example, it could be beneficial to stimulate the brain. So stimulate the brain, for example, the motor cortex. This is where we control our movements. So of our mouth, but also our hands, for example. And we need to move our hands a lot for creating music. And that's also on the motor cortex, but a bit higher up. So you could imagine stimulating those areas would boost the creation of new neurons there, where you're trying to learn. So when you're practicing and boost the neuroactivity, it might happen a little bit faster. So that's something I can think of at the moment.
Yeah, so you would start with the motor cortex for your device. Okay. And there is, of course, a border between restoring function and enhancing already present functions. How do you look at this border? Where do you come across a certain function restoration that you say, well, before we do that, we need to really look into the ethics and have some discussions about that?
Yeah, I think we need to look into the ethics for anything regarding the brain. Also the work that we're doing here, for example, for a speech BCI, this is also can be a problem because we might be capturing people's thoughts and not per se their intention to speak. This is something different because you want people to still be able to think their own private thoughts and not have that all out loud for the world to hear. So this is something we need to take into account from the very beginning in any type of neurotechnology. And I think it becomes even more important when we're looking into enhancement and then how to regulate it. And there's a lot of work to be done on that. A lot of questions there.
And what would the first steps be, in your opinion? So we established this problem, this potentially very huge problem. What do you think is necessary in the first steps?
I think technically we need to implant, when we're implanting for sure, but we need to also make sure that there are safety metrics. So for example, when we're talking about speech BCIs, we need to have a way for the user to still have their autonomy so that they can choose what they want to say and what not. So have a system, a technology in place that allows them to do that. For example, a click in some place or like an on-off switch that they could use from, okay, now I want my thoughts to be decoded, now I don't want it. Besides that, there is the government, for example, and guidelines that needs to be established on how the system should work and what is a border that we should not cross until we figure out more privacy, safety metrics in a way.
Mm-hmm. So on the one hand, safety by design of the device, and on the other hand, by regulation.
Yeah.
Well, I hope the government listens to you, of course. But think a little bit further. Would it be possible to also insert certain functions that we don't usually now have? For example, sensing magnetic fields, for instance, what some birds can do, obviously, or sense infrared light spectrum. Wouldn't that be fantastic?
I wonder.
Or?
I wonder if it's possible, and I wonder if we really need this and if we really want this, because the brain might get overloaded with information that we normally don't have places for to process. So you could think about like the system that could sit on your skin, for example, a sensor that can detect or like work as a GPS and that sends a signal somewhere to tell you what is north. And this is something your brain can learn to deal with and make an association and figure out, okay, when I hear this sound or when I feel this feeling, that indicates north, and this is something that can be used for some form of enhancement. But I think getting the abilities that some animals might have, I think it's a bit far-fetched. I'm not a big fan of this enhancement myself. I think the focus, at least for now, should be on restoring functions for people who have lost it. I think this is what's most important. And then ultimately for enhancing, I think there might be some limited possibilities.
Okay, thank you for your answers.
Sci-fi.
Give the word back to the...
Thank you, Dr. Van Straten. The next opponent is Dr. José González López. He is Associate Professor of Machine Learning and Signal Processing at the University of Granada in Spain. Dr. González.
Thank you, Mr. Prorector. Dear candidate, first of all, I would like to congratulate you and your supervisor and your family for reaching this point. I mean, doing a PhD is sometimes not the most pleasant journey, but you are finally getting it today. Hopefully. I really enjoy reading your thesis. I have so many ideas that I want to try with my group. Also, I want to thank you and your group for releasing the dataset. We are one of these tiny points that you show on the mat today.
2 even.
My biggest concern about your thesis is that I don't share your enthusiasm about rock music and techno that you show us, but that's totally fine. So I do have some questions that are more curiosities that just you to share with us. My first question is about how your work is positioned between the state of the art nowadays in speech PCI. So in speech PCI, state of the art consists of microelectrode arrays that are placed on the motor area. With this, you can get like a 9% error rate. So why would you want to use SEG when you have this microelectrode array that you got so much accuracy?
Highly esteemed opponent, thank you for your words and your question. Yes, that is a good question. There's a lot of advancements that have been made in recent years with those microelectrode arrays. The limitation is that they are very small. They rely on a very, very small piece of the cortex. But if they work very well, that's great. Except not everyone has an intact motor cortex. So what do you do then? You need to go to another area. And this is, I think, where SEG really comes in and gives a benefit, because we can explore these other areas. We can explore the right hemisphere. We can explore other areas within the same hemisphere. And this opens up new potential targets that we hadn't thought of before. And the advantage of SEG compared to other non-invasive neuroimaging techniques that can capture the whole brain is that we do have the temporal dynamics as well, this temporal resolution. So we can really see if we can use this in real time, for example. And that's not something that other techniques can currently do. So I think the benefit of SEG is mostly for really studying these things, exploring new targets, but probably would not be the best for a final BCI at home.
So you already answered my second question. My second question was about the title of your chapter 4. So in chapter 4, you said the title is Moving Beyond the Motor Cortex. So you already answered that maybe you can pick different things. So can you share, because I think I'm the only, maybe with Christian, which is supervisor, the only computer engineer here, so I don't know much about the brain, but can you give some example where looking to other areas of the brain could be beneficial for, like, instance, some disease or whatever that could be affect the motor area?
Yeah, for example, if there's a stroke in the motor cortex, that would be a big reason to look beyond it. Even in neuromuscular conditions, in ALS, it is possible that the motor neurons actually break down at some point. So even in case of ALS, it might be necessary to go somewhere else, eventually, depending on the progression of the disease. People with aphasia, for example, there it depends on, usually also due to a stroke, it depends on where the damage really is in the brain, and then what other region do you want to target. And this is something that needs to be determined per individual, because there are obviously a lot of differences between each individual in terms of the damage. Yeah.
Okay, thank you. I have also a few technical questions regarding how you train your machine learning algorithms. So if I understood correctly, mostly when you train your ML model, you do subject by subject. The problem with that is you normally have data set less than an hour or something like that, while current speech recognition system like Alexa is trained with thousands of hours. So how could you exploit the SEG data you have with data from different patients that have different electrodes? How would you combine that to have a bigger data set and exploit that efficiently for training this model, the AI model?
Yeah, this is a field called transfer learning that I just mentioned briefly, that this is something we're working on in the lab, but it proves to be very, very difficult. And I think that is in part due to the data that we have in terms of that the electrode positions are completely different between participants. So that makes it very difficult to put them all in one. Besides that, there are different neural architectures between people, how their brain is organized, but also what their concepts are, what their preferences are, as we saw with the semantics having different associations. And this is all things that make it very complicated to get to one system that could work for everyone. And even the state-of-the-art models, they are trained are per individual. So they do not have one model and pooling data across individuals. They just have a lot of data for one single patient. And I think this is something that currently is still the best approach. We are working on ways to still combine it. So for example, bringing all the data together and then only focus on the electrodes that are in a certain area and combine those together. So really do it region by region. And this is something that might get us a step further ahead.
Okay, if I have some time, my next question is about this this picture you show us. In this picture, you tell us that different regions of the brain process different part of speech. Do you have results supporting this evidence? Like this little story you show us that behaves like a symphony. You have results supporting this claim?
Yeah, I think this mostly comes from chapter 4 and chapter 5. In chapter 5, we also looked at the temporal dynamics. So we have our tasks. We split this up into different time frames. So we have our neural signals and our speech signals. When we align them temporally together, we can also shift it. So we can use neural features that were prior to the output or after. And then we can do the same process multiple times to figure out if it's either before, slightly before, during, after. And this tells us how it moves across the cortex. And we do see, especially for the semantic properties, we see a kind of posterior to anterior temporal dynamics. And we can also see, but actually what I mostly saw is these core regions. So the motor cortex, auditory cortex, insula are, well, insula is actually a bit later than the rest, but the other ones are active well before we're actually producing our output. And this turns out to be pretty stable, especially in the right hemisphere.
I think we have to move on to the next opponent.
Thank you very much.
I interrupt you. Thank you very much, Dr. Gonzalez-Lopez. The sixth and last opponent is Dr. Sarah Hesham. She is assistant professor in neurosurgery and in particular neuromodulation at Maastricht University. Dr. Hesham.
Yes, thank you, Pro-Rector. Dear candidate, first of all, congratulations to you, your promotion team, and also your family on an excellent thesis. Yeah, when reading it, it was really evident that you really put a lot of work into it. And some chapters I found particularly interesting because I could relate them to my own work. So today I want to focus on chapter 3, 4, and 5. So let's start with chapter 3. As you might know, in our lab, we recently started working with NeurPixels probes. And have also encountered some difficulties related to noise. So NeurPixels probes have hundreds of densely spaced contacts and are also implanted in different tissue types. So including cortical and subcortical gray matter, but also white matter. So yeah, we primarily use these probes in rats, but there's also been attempts to use them in humans. So there was a study 2 years ago. So my first question is, could you explain how your SEG electrodes actually differ from the NeurPixels probes in terms of geometry and signal properties? And how do you think that these differences could influence the choice of referencing method?
Esteemed opponent, thank you for your words and your question. That is a good question. So they're completely different technologies, also working at a completely different scale. So for example, our SEG electrodes, they're quite large, so they capture activity from many different neurons. So we're looking at population level activity. With the NeurPixel, they're very small. And for that, you can get individual neurons. So you can also get the spiking activity. So this is a completely different way of processing the signals, and also in terms of interpretation. So what is what you're actually capturing? Mm-hmm. Yeah, so I think those are big differences. Also in terms of re-referencing.
Mm-hmm. So with NeurPixels, we usually use the common average reference method. Yeah, based on your studies, would you recommend that we continue with this referencing method, or would you actually suggest something else?
Yeah. What frequency range are you looking at? If you're looking at, are you looking at spiking activity or more LFPs?
No, spiking activity, yeah.
Spiking activity. Yeah, and it's difficult because it's a very, very different scale. Mm-hmm. So, for example, when we are looking at the more high frequency activity, we do find a common average. So these larger ways of re-referencing are slightly better. For low frequency, it's more local. Since your technology is much, much more local, mm-hmm. I think the common average might make more sense, except if you're along your grid, if you can see different populations of neurons. So if you can see part of the grid really responding to something and others are not, so if you see differences just by the way you recorded initially, then you might remove a bit of the differences by applying a common average. And you might be inducing some noise as well into other channels that might have had less noise. So I would maybe also test with a method like a bipolar and Laplacian, where you're taking the contacts immediately surrounding the one contact, mm-hmm. and just see what effect this has. But I think you would really have to study that yourself, because these are not that comparable. Okay,
all right, thank you very much. With regard to the time, I will move on already to chapter 4. So I actually was quite surprised that you found meaningful decoding signals from white matter contacts. So how confident can we be that these signals are truly local rather than volume conducted from nearby gray matter?
Yeah, we do not. So it is very likely that it's volume conduction, because in the white matter, or obviously these are our information highways in the brain. So in essence, they carry information. So for sure it could be volume conduction from a nearby gray matter source, or even a distant one. I think there has been some evidence for that, because it travels all along a certain tract. So it would probably depend on which tract you're actually measuring from. This is something that's truly difficult to do. So that's why there hasn't been many focus on this in my work. But yeah, it's a very interesting, I think, area to explore further.
Yeah. And also I saw that the different participants in your study had the electrodes all in different places. So how does this affect the robustness of your conclusions?
I think that is one of the things that makes it difficult to draw conclusions, because especially when we're comparing regions, especially when we're comparing the left and the right hemisphere, for example, when the electrodes are not in a similar place at all, or even within a certain area, this makes it quite difficult. And this is also why I looked at not only accuracy in a certain area, but also consistency. So how many electrodes in that area are actually active. So that tells us a little bit more on if it is only a specific area or even only a specific person, because that's also possible. And some regions are very, very consistent. So for example, the auditory cortex. You would expect this too, because this is really involved in the sound, not only in hearing our own sound, but also in predicting what we want to hear. So yeah, it depends on the areas.
Mrs. Verwoert, as you hear and see, the time for defending your thesis has passed. The committee will now withdraw to discuss the quality of your thesis, in particular the quality of your defense. So please await our return here. Mevrouw Verwoert, de commissie hier aanwezig heeft zich beraden over de kwaliteit van uw proefschrift. En ze heeft ook gelet op de wijze waarop u dat proefschrift hebt verdedigd. En op grond van haar positief oordeel heeft zij besloten u het gevraagde doctoraat toe te kennen, ook gelet op de examens die vroeger door u zijn afgelegd. En dokter Kubbe is gemachtigd u op de gebruikelijke wijze met deze waardigheid te bekleden. Het woord is aan uw promotor, dokter Kubbe.
Belooft u dat u altijd volgens de beginselen van wetenschappelijke integriteit te werk zult gaan, eerlijk en zorgvuldig, transparant, onafhankelijk en verantwoordelijk?
Ja, dat beloof ik.
Krachtens de bevoegdheid ons door de wet toegekend, volgens het besluit van de commissie hier tegenwoordig, verklaar ik hierbij u, Maxime Verwoert, tot dokter te bevorderen en u alle rechten te verlenen die daaraan volgens de wet en gewoonte zijn verbonden. Ten bewijze hiervan overhandig ik u nu de bul, door rector, secretaris en overige leden van de promotiecommissie ondertekend en met het grootzegel van de universiteit bevestigd.
Congratulations, Dr. Verwoert. Congratulations, Maxime. You picked a really adventurous time to start your PhD adventures. We had to interview you online in the first 4 or 5 months. We only worked virtually together. In fact, it took us 6 months to realize your true size. And what we also then realized is your huge creativity. You gave the Neural Interfacing Lab our identity. You designed our logo and you designed our first set of merchandise. Please reach out if you want to buy something. You have so much other qualities. We really, really like your rigor. We really, really like how hardworking you are. I think you set examples for our lab culture. And you're still holding the world record for most recorded patients. And I think it's a record that's very good, very difficult to be beaten. Like every good adventure, your journey had ups and downs. And as the high ups, I want to mention an interview with a newspaper very early and an appearance in a podcast. And I think one of the most frustrating lows was when you got a travel grant to a very prestigious conference that was then moved online. Fortunately, you got the traveling in later. You visited many conferences and you did an internship in Austria where you learned exactly what you don't want to do after you graduated. During our adventures, we also spoke about other stuff than science, and you asked us for advice and then made absolutely sure to never follow our advice. And what you also gave us, and this is, I think, a first for Peter and me, you made us envious of our colleagues in pulmonology because they get to continue working with you, which we unfortunately won't. And we're really looking forward to watching your adventures in pulmonology. Congratulations.
Ja, gaat u maar weer staan hier op het podium. Zeer geleerde dokter Verwoert, beste Maxime. Ik feliciteer je met groot genoegen met het verkrijgen van dit doctoraat. En ik doe dat ook namens de Universiteit Maastricht. En ik zou ook graag een paar indrukken uit de commissie met je willen delen. Ten eerste wil ik je heel graag een compliment geven voor je, wat wij noemen het lekenpraatje. Je presentatie en samenvatting van je proefschrift op een hele gestructureerde en coherente manier. En de universiteit vindt het buitengewoon belangrijk dat je het werk wat hier gedaan wordt goed voor het voetlicht kunt brengen en dat voor een groot publiek begrijpelijk maakt. En ik hoop en ik denk ook wel dat de mensen die hier in de aula en ook de volgers van de livestream zullen ongetwijfeld heel goed begrepen hebben wat je de afgelopen jaren hebt gedaan in je onderzoek. Maar niet alleen dat, ook het proefschrift beschouwen was heel goed. En van een heel goed, kwalitatief goed niveau. En het heeft ook veel interessante en innovatieve aspecten. En we hebben ook gezien een indrukwekkende lijst van publicaties die er ondertussen al zijn verschenen in de afgelopen jaren. Wat de verdediging betreft hebben we gezien dat je, als ik het in een paar kernwoorden mag vatten, heb je dat op een deskundige manier gedaan, heel open, met veel zelfvertrouwen, heel adequaat gereageerd op een grote variëteit aan vragen. En dat heb je op een delicate en op een gebalanceerde manier gedaan. En ik heb ook begrepen, en in ieder geval geldt dat voor mij, ik heb ook heel veel geleerd van zowel je presentatie, van het gedeelte van de proefschrift die ik heb gelezen, maar ook van je verdediging. En je hebt er uitstekend laten zien dat je heel goed in staat bent om zelfstandig onderzoek te verrichten. En dat is waar een doctoraat in feite over gaat. Dus ik feliciteer niet alleen jou daarmee, maar ook je 3 promotoren, dokter Pieter Kubbe, professor Yasin Temel en dokter Christian Herf. Hartelijk gefeliciteerd met het resultaat wat we vandaag hebben gezien. En ik wil natuurlijk ook bij mijn felicitaties betrekken je naaste familie. Je ouders en ook de andere leden van de familie die hier op de eerste rij zitten en waarvan ik hoop dat ze ook hebben genoten van zowel de voordracht als de verdediging. En dat ik wil u daarmee heel graag feliciteren met dit prachtige resultaat. Die felicitaties gaan ook naar de mensen hier in de zaal en de volgers van de livestream, waar ongetwijfeld veel collega's, vrienden en andere familieleden je optreden van vandaag hebben gezien. Ik wil vervolgens graag alle leden van de commissie, I would like to thank, and I do that now, that part in English, I would like to thank all the members of both the assessment committee and the degree committee, because these are not the same people, in part, but not in total. Thank you for critically reading the manuscript and having judged and heard and have posed questions that were very interesting, covered quite a large variety of the field that has been studied, and it had an interesting discussion. So thank you very much. In particular, I would like to thank the external members of the committee. Maastricht University appreciates your contributions. Dan wil ik graag nog even een huishoudelijke mededeling doen. Wij gaan zo dadelijk als eerste de aula verlaten. En ik zou graag willen vragen aan de naaste familieleden om even met ons mee te gaan. Want we gaan in de hal een foto maken en ook met u erbij. Verder wil ik u graag allemaal hartelijk uitnodigen voor de receptie die plaatsvindt in de Refter. U kunt daar naartoe gaan. U kunt dat heel makkelijk vinden als u hier linksaf slaat als u de zaal uitkomt. En u maakt bij de lift een bocht naar rechts, dan komt u vanzelf in de Refter. En daar zien we u later bij de receptie. Hierbij sluit ik deze academische zitting.